Today we are looking at a company that is probably very much below the radar, but which is one of the pioneering companies, not only in the quantum sensing, but also in the quantum communication and in the quantum computing space. So they are probably across the whole quantum ecosystem. And if you want to learn more about pixel photonics, then make sure to stay tuned for today's video as we dive, as always, right into the company within this series of the Hidden Quantum Champions. And with that, let's jump right into what they're actually doing and what this whole video is going to be about. So here we are on the website of Pixel Photonics. It says, let the photon revolution begin, redefining photon detection with SNSPD. SNSPD is a technology that we've seen before. It stands for, as we also see down here, superconducting nanowire single photon detectors. And it basically uses superconductors, which is a quantum material, to detect photons, which are light particles, and with that down to a resolution of single photons. Let's quickly learn a little bit more about those. So harnessing light as a carrier of information is crucial for technology breakthroughs. Innovative technologies are in the need of sufficient scalable, fast and secure single photon detection solutions, and we got them. We have developed a unique approach to combine superconducting nanowire single photon detectors, SNSPDs, with photonic integrated circuits, PIC. SNSPDs already achieve the high detection efficiency, but on top of that, waveguide integration makes our superconducting detectors highly scalable and broadband. Join us as we revolutionize single photon detection in many ways. Want to keep track of our achievements, publications and more, and then there are links to LinkedIn and to their publication page. Okay, so that is already very interesting. We have seen other companies that are active in the space that are talking about superconducting nanowire single photon detectors, SNSPDs. What is interesting here is the combination together with these photonic integrated circuits that we've also seen something about before, and how those go together. And I guess we will learn a little bit more about that as we go through the company's website. So, making photon detection easy, our DINA single photon detector series, the technology behind our single photon detectors guarantees broadband usability, high efficiencies, even beyond the optimized wavelength, and further advantages compared to our other systems. Find out what features our SNSPDs provide and choose between our desktop system and our rack system. And I guess that one here is going to be the desktop version, and that one is going to be the rack, just because of the fact that this sits on top of a desk. Okay, and then what else do we see here? So scalable photon detection, waveguide integration makes the difference. Photon absorption rates of almost 100% at any given wavelength, count rates up to 2 GHz, jitter below 30 picoseconds, a sub-Hertz dark count rate, and the ability to pack several photonic circuits at one single chip demonstrate technology matters. So that was a lot of information. So almost 100% at any given wavelength. Wavelength is more or less the color of your light. So red is usually a high, like a long wavelength. And then on the blue side, on the ultraviolet, you have the short wavelength. And there are like certain wavelengths that are relevant, for example, for communication today. And with the fibers, with the telecommunication fibers that first only spent between the different continents, then also between the, let's say, compute centers, and nowadays even go all the way to your home. So there are specific wavelengths that are relevant here, and the statement here is, okay, what they can do is they don't only need to optimize for a specific one, but what they are offering here is working for almost 100% of any given wavelength. Then count rates of up to 2 gigahertz. So that is kind of, as far as I understand, the frequency at which this can measure single photon coincidences. So how quick is the detector in kind of regenerating itself to a state where it can detect something. The jitter we've also talked before, and then the sub-Hertz dark count rate is basically telling you, okay, how many photons are detected even though there are no photons, and this is in the sub-hertz range here. Hertz is 1 per second, right? And if it's sub-hertz, it means a couple of seconds until you actually have one of these wrong dark counts where there's actually no photon. Then there's also a video here, and then it says the pixel way of doing things. Our company is as specialized as our solutions. In no time, we achieved a revolution in single photon detection and further pursuing the goal to shape the world of tomorrow. This is only possible as a team and with all the individual competencies of each and every one of us. And then, of course, here's the call to kind of join the team, as well as a statement from the founder and partner from Connotation. Good, so let's quickly jump into the products. So we've seen there's a desktop solution, right? And there's a rack solution. It says single photon detection has never been easier. Our DINA detector series. We got one goal, detect and count single photons. Might be two goals, but I understand it's the one and only goal, right? So you want to detect and count them. Therefore, we develop a high performance waveguide integrated superconducting nanowire single photon detector, so WI-SNSPD, enhancing the variability, scalability, and robustness of the photonic integrated circuits and excelling in single photon detection. We want to find out why our DINA single photon detectors are the best. Keep reading, which we will do. So, DINA desktop format, it says desktop version of our single photon detectors comes with a separated helium compressor and therefore produces less heat, noise, and vibrations that could interfere with the photon detection. So that already tells us that here in this case, in order to keep the superconductor superconductive, you need a low temperature. This is reached using a helium type of compressor that is integrated into the solution. So in this case, it comes as a separate box, but it's part of the system. So you don't need to, let's say, have liquid nitrogen access or have even liquid helium access and kind of refill the detector, but it's all, let's say, a closed kind of solution, so much more convenient than actually needing to have access to some liquefaction stages. And then in the rack format, it says rack compatible. This version integrates a cryostat, vacuum system, compressor, and electronics into a single housing, immensely reduces the complexity and size of the single photon detector. So this is kind of what you want to have in what kind of case, right? Versatility versus mobility in this case. Combining the best features in one detector, so broad capability from the visible length of 400 nanometers to the NIR, so wavelength, so near infrared, which is 2000 nanometers. Our SNSPD detectors ensure high system detection efficiency without the need to change the module. Then high scalability. Due to the waveguide integrated approach, our SNSPD technology is highly scalable. This means that hundreds of single photon detectors can be implemented into a single system, consuming only a small amount of space. And then counting at high speed, our SNSPD detectors typically recover in less than 10 nanoseconds. So this is this gigahertz sampling range we saw before, right? And therefore can reach very high count rates even within the gigahertz range. Easy to use, plug and play, single photon detectors, push the button and detector does the rest. You need to no need to install additional parts. Our system comes with all necessary components. That's what I was pointing out before, right? So the compressor and everything is in there. You don't need to kind of assemble things. You don't need to fill up stuff or anything. You just start it, right? After the initial cooldown time, our single photon detectors can operate up to 2.5 years non-stop without maintenance. Photon detection has never been easier. And then waveguide integration, boosting efficiency, speed, and broadband. Our unique approach combines superconducting nanowire detectors and photonic integrated circuits, resulting in the ability to absorb light of any given wavelength to almost 100%. Given the need for more efficient and super fast single photon detectors that are scalable and flexible, waveguide integration for SNSPDs is a quantum leap for photon detection. And here we see, I think, let's zoom in, one of those chips, right? So you see there's some interconnect where you can plug in, I guess, the fiber or fibers, and then you have these kind of little waveguides on the chip that connect now the detector stage with the input, so that you can have like a routing on the chip, and I think that's what kind of sets them apart. And then here it says ensuring 100% quality through in-house fabrication. From the consumer request to the finished SNSPD detector systems, we run through several steps ranging from simulation to in-house fabrication, always looking to meet all the specific requirements. And then, okay, there's more information available there as well. Let's quickly check out one of them. Let's take the rack one, just to see what the product actually looks like, right? So Ardina rack format focusing on usability. Ardina SNSPD rack detector comes at a 19-inch industry rack and stands out because of its reduced size and easy handling. By integrating the cryostat quantum system, compressor, and electronics in one single housing, the system is compact and easy to use. Standard 19-inch rack, easy to use, necessary parts and electronics are included, automated vacuum system, low noise bias and readout electronics, closed loop cryostat, up to 10,000 hours of continuous operation time. These are these 2.5 years, 40 and more channels per system, user interface via Ethernet, and then Python-based API to work with the system, right, on a programming side of things. The operating temperature is between 2.5 and 3 Kelvin, so this will probably not be a dilution refrigerator for the cryostat experts here, but just like a normal helium-4 kind of cooling stage with a 1K pot or something like that attached to it. And then the cool down time is 3 hours, so you turn it on and it takes 3 hours to reach this temperature until you can actually start measuring. There's some more information here about the fiber access. I'm not an expert for that, and readout electronics via SMA. Okay, and the dimensions are listed here as well. So that's kind of what the product looks like. I have not seen one of them in real life yet. The closest that I got was that was before the pandemic. I went to China for a research trip, and we saw there in the institute that they had some of these small compressor systems with fibers connected to it and SNSPDs inside. And I mean, also there, the units are actually quite compact. So as you see, it's 19-inch, so you don't need, let's say, a whole research lab to kind of put this inside, but in theory, you can also just put that in your office space. Of course, generates a little bit of noise because you have a compressor there, so you might not want to have it sitting in your office, but it is not a big machine. And that is important to keep in the back of our minds as we talk about the applications next. And with that, let's hop right into that, because here I think it gets very interesting, because this is where, let's say, the whole under the radar part and the hidden quantum champions part start, because here you will now see how widely ranging this technology actually is within the quantum ecosystem. So here it says one single technology, so many applications, secure quantum communication, absolute security, that certainty that no one can decipher your message. That's the promise of quantum communication, which requires single photon detection to ensure the secure transfer of the key and therefore secure communication over any channel. So quantum communication needs to have single photon detectors, SNSPDs, and that's where Pixel Photonics would, for example, offer a solution. Quantum computing, so now we are up in the stack, right? Quantum computing, faster quantum computing, with photons being one possible foundation for the technology. The detection with SNSPD technology becomes a key part of solving complex problems of the future. Quick note also on that. There are photonic quantum computers. That's of course correct. Another thing that might also be interesting is if you want to, let's say, connect quantum computers, you need to basically have a way to send quantum signals from one place to another. And I'm not saying that necessarily those need to be quantum signals, but it could also be read out signals, whatever. And for that, you might want to have something that can operate on a quantum level, like an SNSPD, but of course, as a distance that is much higher than, for example, from one side of your quantum computing chip to the other. So you might even one day be able, via these photonic connections, to connect different quantum computers to each other. And then, of course, if you have something that is superconducting, that might also be an interesting approach to integrate into existing hardware functionalities. But yeah, not going to go into the details of that, just to point out, besides the normal photon computers, there's also other stuff that might make this interesting. Then it says light detection and ranging, so LiDAR, see the world in a whole new way with detailed 3D maps of the environment. Laser technology and single photon detection enable environmental monitoring, robotics, and much more. So here we come into something that is already a product today, right? So you can buy a LiDAR. Self-driving cars are looking into LiDAR. LiDARs are used in certain security relevant and industry applications. Robots have LiDARs on them nowadays. My vacuum cleaner robot at home has a LiDAR on it and kind of scans with that my apartment and decides which way it has to go. So these things, they are in the application, and of course using those quantum sensors might help to make them even better. Let's say they can, for example, operate on even lower light emissions, right? So there might be some cases where you want to have a very low light LiDAR. So maybe that's interesting for this type of sensors. Then there's single photon imaging. Single photon detection opens up a new world of possibilities, which many fields, including biology, physics, and medicine, as well as astronomy or chemistry. By capturing the smallest signals of light, high-resolution images with incredible sensitivity and precision are created. So today's photosensors and cameras, like for example on your smartphone, they need to collect a lot of photons, right? So that's why you have in a traditional camera this shutter which opens, it collects some light, which then kind of by the sensitivity tuning is being used to create this image. There are certain cases where you might not have that much light, I think, like in astronomy, where you are relying on how much light is being emitted in your direction. So if you have a star that is very far away, you only get a very little amount of light from that. And then you are relying on something that has a very high sensitivity. There might be other cases, and that's where I think probably biology, medicine is more the interesting case, but also in physics, where you don't want to shoot a lot of light on something. Like if you have a little cell and you shoot too much light of it, there's a risk that you can kind of alter the cell, you kill the cell or something like that. In physics, the same. If you shoot too much light on something, you heat it up, you change its properties. So you might need to have very, very little amounts of light. But then you also need to have a detector that can operate on these very little amounts of light. And that's where you need this as an SPDs then, or where you need single photon detectors. And again, now with the technology, I guess, that Pixel Photonics has, with this integrated circuits, with these integrated light circuits, more or less, you can kind of capture the image and then reroute it to these many detectors that you have on your system, and then later on reconstruct the whole image. So you need something that is also scalable, right? And you cannot, like in a classical CMOS detector, at least I guess not for now, you cannot just expose the chip to a little window where like the electrons shine right onto it, but you need to have these fibers that are then kind of steering the light towards the detectors, because the detectors are still, let's say, a little bigger and clunkier, so different from a CMOS chip like you have in your Sony camera today. And then there's space communication, so ultra high speed data transmission from satellite to Earth. This is the promise of laser-based space communication. Our superconducting single photon detectors enhance the performance of the optical ground stations, enabling even higher data transmission rates. And yeah, I mean, that kind of speaks by itself. And I think the space communication is something that we see taking off more and more. SpaceX is creating their kind of network of satellites to offer internet to the world. There are other companies that are on a similar trajectory. I think there are many advantages of this. One, of course, the availability, but then also something that might be less talked about is the actual speed of light propagation of signals. So if you're looking at fibers as we put them today in the ground, within those fibers, the light itself doesn't propagate at the speed of light, but only maybe at, I think, 70%. Don't nail me on that. I'm not an expert of this. But it means that, okay, the information speed is propagating a little bit slower. That is not in contradiction to the Einstein theory of the speed of light being a constant, because here you are talking about the light propagating in matter. But it actually means that if you have a piece of information down on Earth and you have the same piece of information up in the sky in the satellite, and you need to move this to the other side of the planet for something to be calculated, it will probably go quicker if you go via the space where you have the true speed of light versus routing through the fiber on the planet on Earth. And that might be some reason as well to look into this type of technology. At least that's what I think might be interesting about it. But again, not an expert on that. Okay, so now we've talked a little bit about the applications. Let's quickly check out the technology things. So I think we have talked in previous episodes already about the SNSPD, so I'm not going to jump into how that works this time. If you want to see how it works, then check out the Hidden Quantum Champions playlist on our YouTube channel. Link to the channel you find below the video. And there we have talked about other companies in that space and the SNSPDs. But what we want to talk about is the waveguide. So why waveguide integration? With the combination of a nanophotonic waveguide with an SNSPD, we exploit the particular strong absorption of light inside the superconducting nanowire. The efficiency of a normal single photon detector is determined by the thickness of the superconducting thin film and the deposited and mirrors. As waveguide integration maximizes the interaction length of the detector through its traveling wave geometry, we get a photon absorption of nearly 100% at any given wavelength. So as far as I understand this, it's not about, let's say, routing photons on the chip, but more about using the waveguide to kind of create a broadband absorption. What is it called? Like a broadband absorption of the detector itself. So I guess this below here would be the waveguide, like this bar down here, and then this might be the SNSPD up here. And by combining those, you can actually create something that is so the detector that is actually responsive to many different wavelengths. So getting a grip on packaging, so crucial points for high overall system detection efficiencies in single photon detection are, of course, electronic wire bonding and photonic fiber to chip coupling. In both areas, we are eager working to maximizing the performance of our single photon detectors with the goal of achieving overall efficiencies above 90% in the near future. We give high priority to research in these fields in our daily doing as we strive to be in the vanguard of an SNSPD research within all areas. Quick note on that, so photonic fiber to chip is kind of clear. It is how to couple the fiber to the chip without any loss, right? The electric bonding is basically creating the electrical bond between the chip surface, where kind of the superconductor is being evaporated onto, and the outer contacts, so like where your chip is being soldered to, more or less. Trust is good, in-house development is better, since not only the single photon detector itself, but the whole system is highly relevant for performance. We have chosen to develop cryogenic and electronic solutions for the SNSPD systems ourselves. Hence, we use the advances of waveguide integration, embed if requested up to 128 detectors in a single chip, and thanks to in-house fabrication, always ensure the electronics remain low noise. And I guess also low vibration if needed, right? That's the cryogenic side of things. And then there's also an opportunity here to deep dive into their publications. And it also down here says, it also says Pixel Photonics GmbH, so I guess it's a Germany-based company. Let's quickly check out the company. Let's first check out the news and then we check out the company. So stay informed about our latest news. I'm recording this beginning of 2026. Here I see some news from March 2025, February 2025. So yeah, maybe not, let's say, news from yesterday, but I think decently up to date, I would say. And now let's check out the company. So when passion meets endurance, Pixel Photonics, we are a company with a dynamic and vibrant culture that pushes the boundaries of innovation and shares a common goal, redefining single photon detection with SNSPD technology. The Pixel way of doing things, Pixel Photonics, is unlike any other company. We manage an important balancing act. On the one hand, we are keeping the academic spirit up. On the other hand, we have successfully established our DINA single photon detector series on the market within a short period of time. This allows us to keep an innovative mindset as well as deep commitment to our work. And then meet the people behind, and here is a link to the team. So I guess let's quickly check out for that. There's the executive team here with the 3 co-founders as CEO, CTO, and CFO. So that's also very nice to see here that this company consists of people with different focuses and different backgrounds. So you see somebody who's taking the finance as their kind of work, technology, and then as the CEO, of course, you have the overview of the whole company, but also, let's say, the sales side. There's an advisory board here as well, with different people, I guess, also from different backgrounds, scientific advisors. And then there's also a link here to the job vacancies. With that, I want to call it the video for today. If you liked it, and please give the video a thumbs up. And if you have any questions or if you want me to check out any other video, then let me know down in the comments below. Happy to read your comments and looking forward to see you in the next video. Until then, bye bye.